Hello everyone, welcome back to my YouTube channel Z2H Classes. In this video, I am going to discuss few MCQs for BARC written examination. So, in first question, we are asked if there are 3 spin half particle. So, first of all, we are given number of particle, that is 3 number of particles, and these 3 particle have spin half. Okay, so again we are given spin in infinite potential well of length L, then find the ground energy of this system in terms of h square pi square divided by 2 ml square. So in order to solve this question, first of all we have to calculate multiplicity, that is number of state occupied by particle. So number of states occupied by particle, number of state occupied by particle is given as 2s plus 1. Here s is spin. Since we are given that we have spin half particle, so s will be 1 by 2 plus 1. So this and these 2 will cancel and it will be only 1 plus 1, that will be equal to 2. So number of state occupied by particle are 2. So here 2 state will be occupied. So if I take square well potential like this, so suppose this is my potential well, and in this potential well there will be many energy states, ideally infinite energy states. Okay, here we have 2 states are occupied, and again we have 3 number of particles. Okay, in question we are already given that we have 3 number of particle. Since a particle has a spin half, this particle must be fermions, and according to Pauli exclusion principle, the number of particle in one state are those which spin are opposite. So if I fill particle in energy state, there will be in first energy state there must be only 2 particles. One has spin up and another has spin down. So suppose this has energy E1, and in E2 energy level state, E2 energy level, there will be only 1 particle, since we are given only 3 particles in this question. So total energy will be equal to here 2 particles, so energy of this particle must be E1 plus energy of this particle is also E1. So can I write that E1 plus E1 is equals to 2E1, and here we have 1 particle, so the energy of this particle can be written as E2. So total energy will be 2E1 plus E2. So here 2E1 as it is, and you know E2 is nothing but n square E1. So 2E1 plus, I put n as 2, so I will get 2 square E1. So it will be 4 plus 2, so the finally energy will be 6 E1. Okay, and here we are given E1 as pi square h square divided by 2 ml square. So our correct answer will be 6. So option B is correct option. Now move to the next question. In second question we are asked, this is from electrostatic, we are given 3 equal charge Q are placed at 3 corner of square of length A, then electrostatic potential energy at the fourth corner. So here we are given four particle. Sorry, not particle. Very sorry. Here we are given that three charges on square. So if I try to draw, then it will be like this. There is a square, each with length A, each having length A, and there are three particle, or you can say three charge. First one here, suppose, second is here, suppose, and the third one, suppose it is here. And at this fourth point we have to calculate the potential energy. This point here there is no charge, and at this point we have to calculate potential. Okay, so now potential at this point is due to, suppose this is first particle, this is second particle, and this is third particle, or understand by particle I mean charge. Okay, so at this point, potential due to this point is written as, so total potential is equal to, due to this one particle it will be V1 plus potential at this point due to second particle it will be V2, and potential due to third particle will be V3. So V can be written as KQ upon distance between these 2 points. So one particle is here, first particle is here, first charge, you understand, and particle here I mean charge. So first charge has distance A, so it will be KQ divided by A. Second charge also have distance A, so it will be also KQ divided by A. But third charge have distance, this distance, and this distance, you know from Pythagoras theorem, it must be under root 2a. So here I will write KQ upon root 2a. So it will be K2KQ upon A plus KQ upon root 2a. So I take KQ divided by A common, so I will get KQ upon A, and here only remain 2 plus 1 upon under root 2. So it will be potential at fourth corner. Okay, this was our second question. This is from class 12th. Now move to the third question. In third question is from statistical mechanics, in which we are asked that a system of an non-interacting and distinguishable particle. Here you can keep in mind non-interacting particle, that is ideal, and distinguishable. So please remember, when the particle are distinguishable, you have to apply classical statistical mechanics. There are two statistical mechanics. One is classical statistical mechanics when system is distinguishable, and we use quantum statistic when system is indistinguishable. So this will be helpful in interview also. So we are given non-interacting and distinguishable particle of spin 1. Spin we are given, spin is 1. Is in thermodynamic equilibrium, and our system is in equilibrium. So we have to calculate the entropy of the system. So you know the formula of entropy is given as, this is spin, do not forget, this is spin, I write, and formula of entropy I write here, entropy is also denoted by S, so I clarify here spin, And here entropy. Entropy is given as K ln omega. Here K, or you can say Kb, that is Boltzmann constant, ln omega. And what is omega? Omega is number of microstat. So in order to calculate number of microstat, we have to calculate multiplicity. So multiplicity is equals to 2s plus 1. And here spin is given as 1. So I substitute spin 1 plus 1. So multiplicity will be 3. Okay. So multiplicity will be 3. And our omega will be, this is multiplicity, can I denote it as m? Okay, because I take number of particle, n number of particle we are given. So omega will be nothing but omega is equals to multiplicity raised to number of particle. And multiplicity we got here 3. So it will be 3 to the power n. Now substitute number of microstat omega here in entropy equation. So we get Kb ln and number of microstat will be 3 raised to n. Now this is logarithmic, so n will be multiply. So we get 3 Kb ln, n will be multiplied. So here not 3 but shit. Okay, no problem. So here n will be multiplied. So n Kb ln 3. So this will be entropy, n Kb ln 3. So our correct option is D. Now move to the fourth question, and this is from classical mechanic, in which we are asked, let small p small q and capital P capital Q be the two pairs of canonical variable. The transformation capital Q is equals to q raised to alpha cos beta small p, capital P is equals to small q raised to alpha sin beta small p is canonical for. And from option you can see we have to calculate alpha and beta. So in order to calculate alpha and beta, we use canonical condition, and that is you have to remember del capital P divided by del small p multiplied by del capital Q divided by del small q minus del capital P divided by del small q del capital Q del small p equal to 1. Now we have to differentiate, partially differentiate capital P and capital Q with respect to small p and small q respectively. So let us do it. So now del by del small p and capital P we are given as q raised to alpha sin beta p, q raised to alpha sin beta p. So I substitute here q raised to alpha sin beta p, and del by del small q, and capital Q is q raised to alpha cos beta p. So I write here okay, q raised to alpha cos beta p, and again second term will be minus del by del q, and p is given as q raised to alpha sin beta p, and del by del small p, and capital Q is q raised to alpha cos beta p, and it must be equal to 1. Now differentiate partially. So we will get, by differentiating first of all with respect to p. So if we differentiate it with respect to p, then q raised to alpha will be constant. So q raised to alpha as it is, sin is differentiated as cos, so it will be using chain rule also, we get beta cos beta p into, now calculate differentiate with respect to small q, you will get alpha q raised to alpha minus 1 and cos beta p as it is, since p is independent of q. Again, in this term, differentiate with respect to q, and do not forget this sign, minus sign. So I put here minus, and if I differentiate it with respect to q, I will get alpha q raised to alpha minus 1 sin beta p as it is, since p is independent of q. And now differentiate with respect to p, so q raised to alpha will be as it is, q raised to alpha will be as it is, and cos beta will be, cos will be minus sign, so now minus sign, so here will be plus, so beta sin beta p is equals to 1, is equals to 1, is equals to 1. Okay, now let's see what's happened. Again, here q raised to alpha and q raised to alpha minus 1. Here also q raised to alpha, q raised to alpha and q raised to alpha minus 1. Here you can see alpha, here also you can see alpha, here you can see beta, and here also you can see beta. So take it common. So what is common? Beta, alpha beta, q raised to alpha, q raised to alpha minus 1. So what is left here? Cos beta p, cos beta p. So it will be cos square beta p plus, and here sin beta p, sin beta p. So it will be square, and you know is equal to 1. So now this term will be 1. Cos square beta p plus sin square beta p will be 1, and you left only with alpha beta q raised to 2 alpha minus 1 is equals to 1. Here you can see q term is absent, so can you write this, that q raised to 0, and now you can compare the power of q both sides. So it will be 2 alpha minus 1 is equals to 0. That implies alpha must equal to 1 by 2. And if you put, so first of all, look at the options. There is only one option where alpha is 1 by 2. So option D will be correct. I think this example is from Arul Das. Okay, no, sorry, J.C. Upadhyay. Classical Mechanic by J.C. Upadhyay. Now question 5 is a very direct question. In Rutherford, or some pronounce it as Rutherford, elastic scattering cross section varies with center of mass energy E as, this is direct formula, you have to remember it, it varies as 1 upon E square. Okay, so I stop here for today. Thank you very much. Thank you for watching my video, and thank you for supporting my channel.